Of course, of course. I am here.
Yeah, if something, uh, okay,
It's fine. It's fine. Okay, continue.
okay. So I think this is I think what you missed. You see that now.
Good.
You see it?
Yes, sir.
Yes, sir.
Yes, sir.
Yes.
Okay.
Yes.
Clearly.
Okay, clearly. Very good. So this is the definition of the zero divisor graph that I will be using in this talk. And as you see, uh, the vertices are the non-zero zero divisor of the ring, and two vertices are connected if and only if whenever you multiply them you get zero. Okay? And here's some question, uh, which is very natural question. If you have a connected symbol graph, with vertex set V, and assume the number of the vertices less or equal 3, can we find a ring such that the zero divisor graph of the ring will be the given graph? Remember that my graph here is not big. I only have the number of vertices less or equal 3, meaning 1, 2, or 3. And the graph is connected. Can we find? So the answer to this question is yes. What about if I go one more bigger than 3? Like I select number 4 and I have a connected symbol graph and the number of vertices is 4. Can we find a ring such that the zero divisor graph of the ring will be the given graph D? Of course, here read that carefully. What I'm saying here, that D is is a graph with 4 vertices. Just you draw one randomly, not a specific one. Because if you give me a specific one, then the answer will be yes, as you're gonna see later on. But you cannot give me any graph with 4 vertices connected and symbol, and you tell me find the ring, where the zero divisor graph of the ring will be the given graph. Okay? So in general, for 4 will not be correct. Here are some, let me make this, if I can, bigger to see. I think I know how to do this. Yeah. Okay. As you see, the first, here is one, and here is one. Okay, and there is one miss here. You see, if you have a graph with two vertices, connected symbol graph, so it's going to be like, one edge. And the rings that the zero divisor of this ring, uh, uh, which one? Z9. If you go and try to calculate the zero divisor graph of the ring Z9, you will find it's going to be one edge. The zero divisor graph of Z2 cross Z2 will be this. And of course, this is clear. Why? Because you know, the non-zero zero divisor of Z9 only two edges, two vertices, 3 and 6. So that's clear. Because remember, the vertices are the non-zero zero divisor. And for this ring, we have only two edges, 1, 0, 0, 1. And the same thing for this ring. So I mean, this is not I mean, maybe difficult, not difficult, but these are the only rings where the zero divisor graph will give you one edge. And notice none of these rings are isomorphic. So maybe we already answered the question. If you have the zero divisor graph of two rings are isomorphic, does it mean the rings are isomorphic? The answer is no. And here is an example. Here we have three non-isomorphic ring. The zero divisor graph of, for each one of them, I mean, the zero divisor graphs are isomorphic, but the rings are not isomorphic. Okay, here is also uh, the zero divisor graph of order 4. Because remember what I told you, if you just give me a graph, a simple connected graph with 4 vertices, and you tell me find the ring where the zero divisor graph is that ring, it's not, the answer is no. What I mean with no, we cannot always find a such ring. But if you give me specific graph with 4 vertices, then the answer is yes. Like, this is specific one. We have 4 vertices, 1, 2, 3, 4. This is another one, and this is another one, right? For these, yes, I can give you the rings. But like if I remove one diagonal, imagine you remove this diagonal here in the middle. If you remove the diagonal, one diagonal in the middle, you still have a graph with 4 vertices. But I cannot give you the ring. There is no such ring. So for vertices, for a graph with 4 vertices, these are the graphs where I can find a ring, and the zero divisor graph of the ring will be the given graph. Okay. All right. And I will mention a few things here. This table here. Okay, let's see how you're gonna read it. The number of vertices of the graph is 2. And what are the rings that will give me that have vertices with 2? Sorry. So this column here is the number of vertices. Here are the rings where the non-zero zero divisors will be the number of vertices, like Z9 here. Z9 has 9 elements. We know that. How many non-zero zero divisor does Z9 have? 2. And how the graph look like? K2. What's K2 mean? Complete graph with 2 vertices, 1 edge. Okay? All right.
Yes, sir.
Okay. So you still hear me and everything is fine?
Okay, sir. Fine,
Yes,
fine.
sir.
Okay.
Yes,
Yes, sir.
yes.
Yes, sir.
Okay.
Yes, sir.
So you look at this table here, like the number of vertices 3. Then you want to know all the rings Non-isomorphic rings, of course. If you see this under ring, you see many rings. All these rings are not isomorphic. Okay? Definitely Z6,
Yes, sir.
Yes,
Z6,
sir.
Z6 will have three vertices. Why? Because the non-zero zero divisor will be 2, 3, 4, three vertices. Z8 will have three vertices. Okay? And here on the graph, it tell you what kind of a graph you get. So look, for Z6, you get the graph complete bipartite, K12, where Z8 will give you the graph K12, K12, and then you have K3, complete graph, and so on. You go like to 4,
Yes, sir.
okay? So you see this kind of work been done, and in fact, maybe I should mention, go back, the name of the person who did that, if I can. Seems I removed that. Is not, or maybe it's coming after. Yeah, you see the remark here. Ridman, he has two papers. In the second paper, he corrected some mistake in the first paper in 2007 on the zero divisor graph of a small finite commutative ring. He was able to characterize, I think, up to 30, like the number of vertices equal 30, and he gave all the rings and so on. Okay, so there is some, as you see here, 14, oops, up to where I have written here. So he's giving, yeah, I don't know what's going on. Anyway, yeah, I think it's given up to 30, but I believe this work is not complete to my best knowledge. So if you are a student, maybe you can check the last number known, maybe 30 or 40. I'm not sure really about that. And there is some work. And of course, you need to use maybe some computer there. So here is the question, like given a number n, let's see 110, okay? Can you give me uh, all rings where you know, the non-zero zero divisors will be 110, and can you give me how the graph look like? Just like in this table here. Okay, so you see this is not easy question, and it's I don't think it even maybe you need a group work, involve a lot of work and a lot of computational thing. Anyway, okay. All right, so let's start with some basic properties of the zero divisor graph. What are these basic properties? Like the zero divisor graph is a star graph. What does it mean, a star graph, by the way? Meaning, you know, like you have one vertex connected to every other vertex, and all other vertices, none of them is connected to to another one. It's just like K1n, K1n, complete bipartite graph where one of the sets has only one vertex. So in this theorem help you a little bit in working with like, okay, look, what the zero divisory graph is a star graph if and only if R has to be isomorphic to Z2 cross F. Okay? And remember, R is finite ring, where F is a finite field. So if the zero divisory graph is a star graph, then we know how many elements, the number of the vertices. And remember that the number of vertices are the number of the non-zero zero divisor of the ring. Okay? So what that tell me? Tell me if you are looking at a ring with 15 element, then definitely the zero divisory graph will not be star graph. Why? Because definitely the number of the zero divisor will not be prime to the n. Remember, I selected my ring to have 15 element. Anyway, okay, all of you, okay. So I need to define the girth for you. What do I mean? Yeah, I think I'm missing something here. Yeah. What do I mean with regular graph? A connected symbol graph, we call it regular if and only if all vertices have the same degree, right? If all vertices
Yes,
have
sir.
the same degree. Okay, can you give me
Yes, sir.
examples of regular graph?
A
Well,
square.
s- square, yes. KNN, KM, complete bipartite or complete graph, or if you have a cycle with n bigger or equal 3. A square is a cycle, as you said. There are many
Yes, sir. It's a
graphs,
cycle. A circuit.
yeah, a circuit. There are many graphs that are regular. Look what we have here. In this paper, 2004, by Saeed Akbari and Muhammad Yan, they are Iranian mathematician. They show that if the zero divisory graph is regular graph, then it has to be either complete or complete bipartite. Okay? So for the zero divisory graph, if the zero divisory graph is regular, then it has to be complete or complete bipartite. Okay? All right. What do we mean with
Okay, sir.
what do we mean with girth? The girth of a graph is defined to be the length of the shortest cycle. The length of the shortest cycle. And remember how we measure the length. The length will be the number of edges you are using in the cycle. So a triangle is like we say this is a cycle of length 3 because I have 3 edges. A square will have girth 4 because I'm using 4 edges. So in general, if you have a connected graph, then the girth of the graph will be the length of the shortest cycle. If the graph has no cycles, then we say the girth is infinity. And you know many graphs that have no cycle, like trees. When you have a tree will not have a cycle. So the girth will be
Yes.
infinity.
Okay.
Okay,
Yes, sir.
okay. In this paper in 2007, David Anderson and Molay, the following statement are equivalent for a reduced commutative ring. What do I mean with reduced commutative ring? I mean reduced. Reduced ring mean the 0 is the only nilpotent element. What do I mean with nilpotent element? Like x to the n equals 0, then we call x nilpotent. Reduced mean x to the n equals 0, then x has to be 0. Okay? So that's the definition of a reduced ring, meaning 0 is the only nilpotent element. Okay? Like Z8 is not reduced. Why? 2 cube equals 0. 4 square equals 0, right? In Z8. So Z8 is not reduced, where Z6, Z10, Z14, these are reduced. Okay, the following statements are equivalent for a reduced commutative ring. The girth is 4. The zero divisor graph has to be a complete uh, bipartite graph. Look at C. Number B, this is the total quotient ring. What do I mean with the total quotient ring? This is localizing R at the set of all regular elements of R. Or if you wanna, uh, you can remove that and you can say that R is isomorphic to a cross product of two integral domains. Here the characterization is given uh, in terms of a total quotient ring. So another way to say that R is a subring of a product of two integral domains. Okay? All right, look,
Okay.
in this result here, in this result here, uh, the characterization for the girth to be 4 is for reduced ring. So you're gonna ask me, what about if the ring is not reduced? Then the girth 4, R will be isomorphic to D cross B, where D is integral domain, and B has to be this ring or this ring. So if the girth is 4, we know how the ring look like. Okay? All right. What about uh, if the girth is infinity? Meaning what? 3, meaning we don't have cycle. For a reduced commutative ring, these are equivalent. the graph is non-empty and the girth is infinity, then we know the total quotient ring look like. Or as I told you, this another way to say that R is a subring of a product of two integral domain, because here I'm using the total quotient ring, TR. Or the graph, of course, this is. And the same thing if the ring is not reduced. Okay, here is a question. Assume the zero divisor graph is complete. What can we say about the zero divisor graph of the polynomial ring? The answer is no. If the zero divisor graph of the ring R is complete, that does not mean the zero divisor graph of the polynomial ring is complete. And here is the example. If you can look at this, but the answer is no. Okay? Now, let me remind you what we mean with the diameter of the graph. First thing, we need to know what we mean with the distance of the graph. The distance measured to be the length of the shortest path from X to Y. And remember that how we measure length. We measure length by counting number of edges we use to go from one vertex to another. So when you tell me this is a path of length 3, I know that I can go from E to B by crossing 3 edges. So the distance is the shortest path that would take me from X to Y. The diameter of the graph, if you take the maximum of all distances, or the supremum, okay? That's the definition of the diameter of the graph, is the supremum or the maximum of all distances. Okay, Locus, he gave a characterization uh, for diameter. In fact, maybe I did not mention, but I will mention that to you now. It turns out that the diameter of the graph is either 1, 2, or 3, not much. So that means whenever you have a ring and you want to go from one vertex to another, the maximum number of edges you're going to cross is 3. Okay, of course you can, do that by 50 maybe. But look, the distance between two vertices is the length of the shortest path. I mean, maybe I can go from A to B by crossing 10 edges, and you can go by crossing 4 and 2. So in this case, the distance will be 2. Okay, and the diameter is the maximum of all distances. And the theorem says that the diameter cannot be more than 3. So the diameter is either 1 or 2 or 3. Okay?
Okay, sir.
Okay. So look at this result here. If the ring is reduced and the zero divisor is not an ideal, then the diameter is always less or equal to 2 if and only if R has exactly 2 minimal prime ideal. What that mean? if I gave you R to be a product of two integral domain, like if I told you R equals Z5 cross Z11, quickly I know that the diameter is going to be 2 of this graph. The zero divisor graph of Z5 cross Z11 will be 2. Why? Because the ring Z5, Z11 is reduced, okay? And by this theorem, the diameter is going to be 2. Okay, I'm going to talk about a little bit of how many minutes left for me.
45 minutes.
How many?
45 minutes,
Okay,
you mean?
okay. Okay, I'm going to talk about the annihilatory graph that was introduced by Ayman Badawi in 2014. And I'm going to talk about the annihilatory graph and its connection and how this graph is connected with the zero divisor graph. So here is the definition. Again, if you want to follow my talk, you need to know what I mean with the annihilatory graph. So annihilatory graph of a commutative ring is a symbol graph, and this is the notation we're going to use. With the vertex set will be the same thing, the non-zero zero divisors of the ring. Okay? So the
Yes,
vertices
sir.
will be the same thing as the vertices of the zero, and two distinct vertices, x and y, are adjacent if the annihilator of xy is not equal to the annihilator of x union annihilator of y. This is how we connect. Okay, what do I mean with the annihilator of an element? The annihilator of an element, like, okay, let's choose an element A. What do I mean with the annihilator of A? I mean all the elements in the ring, call them B, where BA equals 0. In the street language, the annihilator of A means all the elements in the ring R when you when you multiply them with A, you come up with 0. Okay? So the annihilating of A means all the elements in the ring. When I multiply these elements, when I multiply each one of them by A, I come up with 0. So the annihilator of xy not equal to the annihilator of x union annihilator of y. If this is the case, then we connect. Okay? All right. Uh, Here are some properties on the annihilatory graph. It's always connected, and of course, all of us know what that means, connected. That means you can always go from one vertex to another. What's interesting is the diameter is smaller than the diameter of the zero divisor graph. The diameter is less or equal to 2. Okay? The diameter is less or equal to 2, the diameter of the annihilatory graph.
Okay.
Okay, and
Okay.
if you look at number 2, the annihilatory graph is the same as the zero divisor graph if and only if R has exactly two distinct minimal prime ideal. And in number two, the assumption that the ring is reduced. So if you have a reduced ring, then these two are the same if and only if R has exactly two distinct minimal prime ideal. You're gonna tell me, can you give me an example? Yes. Like take your ring to be Z5 cross Z11. Take R to be a product of two field. Okay? I mean, if you wanna, of course, I mean, in practice, a graph are finite. So maybe if you wanna do it from a practical point of view, maybe you can choose your ring to be finite, like R to be Z5 cross Z11, Z5 cross Z7, you know, okay? So a product of two finite field, there is no difference between the zero divisor graph of the ring and the annihilator graph of the ring. They are equal. They are the same, according to this theorem. Uh, Let R be a reduced ring and assume that the zero divisor is an ideal. If the zero divisor of the ring is an ideal, that means the set of all zero divisors of the ring is an ideal, okay? Then these two graphs are not equal. The annihilatory graph and the zero divisor, and the girth has to be 3. Okay? Here, what do I mean with
Yes, sir.
non-reduced? Non-reduced mean x to the n equals 0 has at least one non-zero solution in the ring. So non-reduced is the opposite of reduced. Remember that reduced mean x to the n equals 0 if and only if x equals 0. Non-reduced mean x to the n equals 0 has at least one non-zero solution to the equation x to the n equals 0. Okay, if the ring is non-reduced, and you nil meaning the set of all nilpotent element of the ring, then these two graphs are not the same and the girth is 3. Look at number 3, 5. If the ring is non-reduced and the zero divisor is not an ideal, non-reduced, then these are not the same. The annihilatory graph and the zero divisor graph are not the same. Okay, let's take this example. This here a product of three finite field, Z3 cross Z5 cross Z7. If by doing maybe minimum algebra, you know that R has three minimal prime ideal. This ring has exactly three minimal prime ideal. And the ring is reduced. So that means these are not the same because the ring is reduced and the ring has three minimal, then you cannot have the zero divisor graph the same as the annihilatory graph. Why? By this theorem. Look at this theorem here. Number 2, look at number 2. If the ring is reduced, then the annihilatory graph is the same as the zero if and only if R has exactly two distinct minimal prime ideal. Okay?
Okay, sir.
All right. Here, I will just stop. I mean, there are more. You can, if you need these, I mean, I have this paper. In fact, it's a free download. If you go to my personal web page, you will see all my papers. And it's a, like a free download. If you want to read more about the annihilatory graph, you can read more. So I want to kind of strange, you're going to see why I mentioned that here. It's kind of strange how the connection between this concept and the annihilatory graph. Okay, I only need to give you the definition. What do I mean? In 2007, I gave this definition of two absorbing ideal. What do I mean with two absorbing ideal? A proper ideal, we call it two absorbing if whenever you have three elements in R and the product ABC in I, then I want AB in I or AC in I or BC in I. This is like a generalization of a prime ideal. Because what is the definition of a prime ideal? Prime ideal mean whenever I have a product of two in I, then one of them has to be in I. Here, what I'm saying, whenever I have a product of three element in I, then a product of two should stay in I. Okay? Look at this very nice connection, which is recent, relatively speaking. In 2018, uh, I think they are Iranian mathematician in the Indian Journal of Pure and Applied Math. They made this connection. Remember that in the paper I told you about where I introduced the annihilatory graph, I have like cases, like when the ring is reduced, when the ring is not reduced, and so on. But they gave no restriction on the ring. The only restriction R is a commutative ring. Then the zero divisor graph is the same as the annihilatory graph if and only if 0 is a two absorbing ideal of R. So they made a connection between two absorbing and the annihilatory graph and the zero divisor graph. That was when I saw that, I was really, I mean, this is very beautiful result. Uh, I mean, it's amazing if you know what I mean, how this is connected. I mean, what's two absorbing has to do with the graph. But it turns out that these are the same if and only if 0 is a two absorbing ideal of R. Very nice result. Okay? All right.
Yes, sir.
Okay, here is I think this is my last result on annihilatory graph. Assume that the annihilatory graph is not equal to the zero divisor graph. So that's the assumption. Then the following are equivalent. Look at number 1. If you tell me the girth of the annihilatory graph is equal 4, this is exactly if you are telling me that the girth is not equal 3. Look at 1 and 2. And number 5, I know how the ring look like. R is isomorphic to this ring or this ring. Okay?
Okay, sir.
That's a very nice characterization of, Anyway, for non-reduced commutative ring, the following are equivalent. The girth is 4. Look at number 4. I know exactly how the graph look like. 2, 3. Complete. Let R be a non-reduced. The girth is 4. Equivalent. I know how the graph look like. And I know how the ring look like. If you tell me, if you give me the ring is non-reduced, then these statements are equivalent. And here, as you see, there are not many rings. R has to be to isomorphic to this or this. Okay. All right. Now I will be switch to another recent, very recent. In fact, this paper did not appear yet, but I thought I will talk with you about it. Can you see?
Yes,
Yes,
yes.
sir.
Yes, sir. Yes, sir.
Yes, sir. Yes, sir.
Okay. This has to do with Ramsey number of a graph. This is a paper that is, I told you, did not appear yet. It get accepted. Maybe it will appear online by the end of this month with my co-author, Rosie Risner from Austria. And we study the Ramsey number. Okay, okay, so you want to know what I mean with Ramsey number. Here is the question. It started like that. Imagine that you went to a party, like gathering, and you ask this question. I want to know like the minimum number of the people in the party. Let's call it K, the minimum number, so that you can claim quickly there are at least 6 people in that party, they know each other, or there are at least 6 people that they do not know each other. Okay? This is kind of a question that, these are very difficult question. In fact, Ramsey number uh, for some graph, I'm giving you now, like street language implication of the Ramsey number. But okay, let's get to it. What I mean with Ramsey number for a graph. Here is the simple definition of Ramsey number. Give me a graph. I mean, no, not give me a graph. I need to choose the minimum number of vertices I need. Watch again. The number of the minimum number of vertices I need so that I can claim that n of these vertices form a complete graph. What I mean complete, that mean every two connected, or m vertices where none of these m vertices are adjacent to each other. Okay, I'll repeat that again. Choose two numbers, call them n and m. Like, let's choose, like, one is 7 and one is 5. So I choose 7 and 5. And my question, what is the minimum number of vertices I need in a graph so that I know there will be 7 vertices will give me a complete subgraph, or 5 vertices where none of these 5 adjacent to other remaining vertices. Okay? All right. But here we did not study it for all graph. We only study the Ramsey number for partial order graph. What do I mean with partial order graph? Partial order, first thing you need to know what we mean with partial uh, order on a set. The things we study in, undergraduate, that a relation, we call it a partial order if it satisfies 3 axioms. What are these axioms? That A equal A, each element equal to itself. The second, if A less or equal to B, and A and B are distinct, then B is not less or equal to A. Anti-transitive, I think they call it. No, anti-symmetric, maybe. Yeah, anti-symmetric, maybe. Yeah, okay. And then the third
Yes.
one is the transitive. If A less or equal to B, B less or equal to C, then A has to be less or equal to C. A partial order relation that you study undergraduate. Okay, so the partial order graph, how do you form a partial order graph? Here is how you form it. First thing, you need a partial order relation. We call it usually less or equal. Then you define your partial order graph to be a symbol graph, such that two vertices are connected if and only if A less or equal to B or B less or equal to A. Okay? This is how you,
Yes, sir.
so you have a partial order graph, first thing on the set. And then you define the graph. And how you define it? You define it as I told you. Two vertices are connected if A less or equal to B or B less or equal to A. And there are many. Okay, here is the first one. If I take a commutative ring and I take V be the set of all non-zero elements of R. Proper here meaning non-zero, and they are not unit, they are not invertible. Because we know if we have two invertible elements, then they always divide each other. So proper element here, meaning non-zero and non-unit. And you define this relation on V. How? A and B in V, we have A less or equal to B if either A equal B or A, you see double vertical here, meaning A strictly divide B. In another way, that if A divide B, then B does not divide A. That's what double vertical line mean. That A is a factor of B, but B is not a factor of A. All right? Then definitely under this
Yes, sir.
relation, this graph become a partial order graph. All right? All right. So the question,
Yes, sir.
okay, here is it. Let n m bigger or equal 1 need not be distinct. What do I mean with the Ramsey number? Okay, so now you know how my graph look like. All right? In fact, let me go, I mean, for lemma 2, you really, I mean, you don't really even need maybe a ring here. Anyway, let me give you a simple case for lemma 2. Take all positive integers. Take all positive integers, like z plus, and define exactly what I mentioned here, that 2 A and B are two positive integers, then we say A less or equal to B if A equal B or A is a factor of B. Then definitely this is a partial order on the set of all positive integers. Okay, here is the question I want to answer to make it simple without using math, you know. Give me N and M, all right? N and M. Like let's choose 8 and 9. 8 is my N, 9 is my M. I want to know the minimum number of elements I can select from Z plus so that I will have at least 8 numbers. Let's call them A1, A2, A3 up to A8, where A1 is a factor of A2, is a factor of A3, is a factor of A4, is a factor, keep going till you reach A8. Or I will have 9 numbers because I selected N to be 8 and M to be 9. Okay? And again, what I need the minimum number that I can select randomly from the positive integers, where I will have 8 elements, at least 8, where each one is a factor of the other, like A1 is a factor of A2 is a factor and so on. Or I will have 9 numbers where none of them is a factor of the other 8. None of them is a factor of the other 8. So I will have 8 or 9. So how many numbers I should select? The minimum number that will achieve this goal. Or here is another question. Let's talk about the same thing. Uh, uh, I want to know, let's change n to 5 and m to 4. 5 and 4. So what's the question become? What is the minimum number of positive integers I should select so that I will have 5 numbers, call them A1, A2, A3 up to A5, where A1 is a factor of A2, is a factor of A3, is a factor of A4, is a factor of A5, or I will have 4 numbers, call them B1, B2, B3, B4, where B1 is not a factor of the other 3, and B2 is not a factor of the other 3. So none of them is a factor of the other. That's a very interesting. I mean, this is the implication of the partial order graph. We were able to calculate the Ramsey number for this class of graph, which is a partial order graph. Okay? And what is the answer? Here is the answer. Forget this notation. So remember that in the first question I asked you, what is the minimum number of vertices I should select? The minimum number of positive integers I should select, where n numbers I will have n, where each one is a factor of the other, like A1 is a factor of A2, a factor up to AN, or I will have m numbers where none of these numbers is a factor of the remaining one. And it turns out that's the answer. I mean, the proof of that, I mean, you have to be tricky in a way. Anyway, if you want to see the proof, you can. I think this paper also is on my personal webpage. That's the answer to the question. So that means in the first question, when I ask you, like I have 8, I selected n to be 8 and selected m to be 9. And I want to know the minimum number of positive integer I should select so that I will have 8 numbers where A1 is a factor of A2, is a factor of A3, is a factor of A4, and so on up to I reach A to the 8. Or I will have B1 is not a factor. I mean, I have 9 numbers, B1, B2, up to B9, where none of the BIs is a factor of the other BIs. Okay, the number will be 8 minus 1, that will be 7. 9 minus 1, that will be 8. So 8 times 7, 56, and you add 1, 57. And remember what I'm telling you. This is the minimum number of positive integer you should select in order to have 8 numbers where each one is a factor of the other, like A1 is a factor of A2, is a factor of A3, is a factor, and so on. Or you have 9 numbers out of the 57 where none of them is a factor of the other. The minimum number is 9, is 57. And let's think about it. Well, if you select 56, it will not work. because I can select 56 numbers where what I told you will not be true. So you see the beauty of this result, that will give you the minimum number that you should select. And the minimum number is exact. It tells you it has to be n minus 1 times m minus 1 plus 1. Okay? All right, so if you want to have another example, you still with me? You hear me?
Yes, sir.
Yes, sir.
Yes, sir.
Okay.
Sir.
Yes, sir.
Yes, sir.
Okay, so let's take
Sir,
another.
are there any significance in the, sir, one question. In the notation you have used, R diverge G, or are there any significance in this notation?
No, well, the significant, because I'm using different partial order relation. Here I'm using div.
POG.
Yeah, here
POG stands for
is,
partial order.
yes, this is in general. This
Yeah,
is
yeah.
for all partial order graph. In fact, I try
Okay,
to
okay.
make it more, brief, uh, because we calculated the minimum for all partial order graph. And then we start looking at the special cases. But in this talk, I find to talk about the special cases is more useful. And if you want to know the general, in general, you can go and read that paper or just email me and I will send you the paper. So the paper was not only for integers. We calculated the partial order, this Ramsey number for all partial order graphs. And then we start taking subclasses. Like one of them is the one I just told you about. To make the story, I mean, the same question I ask you, you can answer it if you choose n to be 7 and m to be 3. What do I mean with 7 and 3? I need to find the minimum number of positive integers. The minimum number of positive integers I should select randomly so that I will have at least 7 numbers, A1 up to A7, where A1 is a factor of A2 is a factor of A3 up to A7, or I will have B1, B2, B3, where B1 is not a factor of B2, B1 is not a factor of B3, B2 is not a factor of B3. Okay? The smallest number that will is 7 minus 1, 6. 3 minus 1 is 2. 2 times 6, that will be 12, 13. So if you select randomly 13 numbers, you should have, in this selection, you should have 7 numbers, A1 up to A7, where A1 is a factor of A2 is a factor up to A7, or you should have 3 numbers where none of them is a factor of the other 2. Okay? Okay, and this formula here, I use it for many. Here is another inclusion. If you are in ring theory, uh, you can build a graph. They call it the inclusion graph. And such a graph is studied by Saeed Akbari, inclusion graph. What does inclusion graph? It turns out the inclusion graph is a partial order graph. Your vertices will be the set of all ideals, left ideal. Since my ring is commutative, I can say a set of all ideals. Okay? And how you connect A and like two ideals are connected, I and J are connected if and only if one of them is a subset of the other. So again, that will give you, and here look, proper inclusion, not proper or equal, in order to have partial order graph. Okay? And it turns out this graph satisfies the same formula. So what is the question? The question maybe it should be, here is it. Let R be a ring and N and M bigger than 1. And you take S to be I. Forget left and right. You can say, because my ring is commutative, I is an ideal of R. And assume that the set S, not A, that's a mistake here, this A should be S, is bigger or equal to this number. Okay? Then one of the following must hold. You should have exactly n ideals where I1 is a subset of I2 of subset of In, or there are m ideals where none of them is contained in the other. Okay, so let's see. Z is a ring. Let's take Z, the set of all integers. Okay, and the question, how big my, and choose n to be 5 and m to be 4. 5 and 4. 5 and 4. How many ideals I should select? The minimum number of ideals I should select will be 5 minus 1, 4. 4 times 3 plus 1, 13. If you select 13 ideals, distinct ideals in Z, what you should have? You should have, we said 5 and 4. I should have 5 ideals. Again, this A is supposed to be S, or change S to A. You should have 5 ideals where I1 is a subset of I2 is a subset up to I5, or you should have 4 ideals out of the 13 we selected. So I went to Z and I selected 13 ideals, 13 randomly. Then I should have this, or I should have this. These are implication of what I call the Ramsey number, the implication of the Ramsey number. Okay?
Yes, sir.
Okay.
Yes, sir.
And the same thing, another graph, we call it the idempotent graph. It's going to be the same thing. The same thing. Okay. Here I will finish up. How many? I mean, do I have 10 minutes?
You have 1 or 2 minutes left.
Okay. So maybe I think I had enough. If you are this paper already on my personal web page, free download. But if you want it, just send me an email and I will send you this paper. And I thank you for listening, and I'm done. Thank you.
Thank you.
Thank you, sir.
Thank you, sir. Thank you very much.
Thank you, sir. Thank you.
Thank you,
Thank you,
sir.
sir.
Thank you. Thank you very much, sir. Your
Thank
nice
you.
talk.
Thank you very
Sir,
much.
share your PPT, sir.
Thank you, sir.
Thank you, sir.
Thank you.
Sir, please share your PPT, sir. Please.
Sorry?
Please share
Thank you
your
very
PPT,
much,
sir.
dear participants. Please.
Sir, actually, I have one question.
Sure.
Excuse me, sir.
Sure.
Sir, very good afternoon. Sir, actually, you have told the distance between two vertices. That means if